All right, we'll go ahead and get started for today. Today is March 11th, Thursday, and this is Civil Engineering 481 or Transportation Engineering. And today we are going to continue on with Chapter 5, and we're going to talk about traffic flow models today. In particular, we're going to be focusing in on the Poisson distribution in today's class. Just to let you know, I posted the slides for today's class and just published them, I don't know, a few minutes ago in Canvas. And I also have the homework assignment for Chapter 5 should have posted at 4 o'clock as well a couple of minutes ago. And that's the homework for Chapter 5. It's like 4 problems, I think, and it is going to be due a week from today on the 18th of March at just before class starts. So kind of the same way we normally do things as far as that goes. And let me see, at least 2 of the problems are going to be based on things that we covered on Tuesday and today. 1 or 2 of the problems might be a little bit more focused on what we'll cover on Tuesday. So anyway, you can look ahead in the chapter and look at some of the problems if you want to get a head start on those, but we probably won't cover all of the material to be able to cover all of the homework problems until next Tuesday, which is the 16th of March. So any questions on anything before? Oh, one other thing, I'm gonna, at the end of the class today, after I'm done with the Chapter 5 slides and problems, etc., I'm gonna spend a little bit of time, and if you look at the class slides that I've posted, the very last slide is just a potential timeline for working on your group papers. So I just wanted to spend a little time talking about that. I mean, the group papers are due on April 27th, so it's a month and a half away, but I think, I just want to get all of you thinking about, the timeline for being able to get the work done for your group papers. So I'll talk about that at the end today. And just a reminder, the groups that you will use for the paper is the same groups that you did the first group 1 assignment or group assignment a couple of weeks back. We're also going to have 1 other group assignment coming up in a couple of weeks, I guess. Yeah, 2 weeks from today, we're going to have our second group assignment, and then we'll have the group paper and the presentation of the papers. And so those will all add up to the group assignments for the class. Okay. And I guess the last thing I'll talk about that's just about the class itself, I was asked by the department to post this link to a survey, and I posted it as I was told, and then of course one of you let me know that the link didn't work. So I had to pull it down, checked back with the department coordinator, and then she sent me a link that I tested and it looked like it did work to me. So I reposted that. So if you guys have the opportunity to take that survey, that's something that's helpful for the department as they go through their AVET certification process. So I'd appreciate everybody associated with the civil engineering department would be grateful if you would take that survey. Okay, any questions before we go ahead and get started on the next portion of Chapter 5? Okay, let me go ahead and start sharing my screen. And here we go. All right, and then let me also do this. Okay. All right. So what you see on my screen here is the slides for today. The models of traffic flow is what we're going to be talking about. And then over here, I've got this, if you recall, on Tuesday, I went over this document over here on this side of my screen, which has all of the various equations that we went through on Tuesday, the definitions of Q and of flow and speed and density, and then the relationships between speed and density and flow and speed over here. And today we're gonna go over these equations here involving arrival rates of vehicles as applied to vehicles and using the Poisson distribution. Maybe something you've seen in your, if you took a statistics class, you may have seen this before, this concept, but we're going to go over it because it does apply directly to a lot of traffic analysis that's done in for highways and intersections and things like that. So that's what we're going to be covering today. So this comes right out of your book, and there's just, and again, this is the file that I posted in course documents in Canvas. So just something to keep in mind as we go along. So we talked a little bit about this on Tuesday, that there's two ways to look at traffic analysis for for planning for highway systems and so forth, at the macroscopic level and at the microscopic level. So macroscopic level is kind of looking at the system as a whole. Microscopic level is kind of pulling it apart and looking at the pieces, more or less. And so the traffic analysis, as it says here, a lot of it is focused on the microscopic level, and particularly the elapsed time between the arrival of successive vehicles, which is, as we talked about on Tuesday, the headway. And headway is a measure of time, not of space. Spacing is a measure of distance. Headway is a measure of time, how much time there is between the arrival of two vehicles. And this is, as it says here, very essential to the queuing analysis or queuing theory that you use in various analysis processes. Now, as it says here, the simplest way to look at modeling vehicle arrivals, right? And vehicle arrivals are important. How often and how much and how many vehicles are going to arrive in what period of time can affect signal design. It can affect, if you're working on sizing a parking lot for a development, all sorts of things that in terms of planning for the appropriate number of vehicles in a given time frame. I mean, and so the simplest way to do that is just assume there's a uniform spacing. Arrivals come, there's 5 vehicles per minute, and that continues on all day long. And so that's a deterministic, as they say, arrival pattern. There's a constant headway between all vehicles in that case. But that assumption isn't always realistic because a lot of times vehicles arrive randomly. And so if vehicles arrive randomly, how do we deal with that? And one of the ways to do that is to look at a model that represents a random arrival process in order to do that. Probably important to just to clarify the definition of random. So first, as it says here, so if a sequence of events is truly random, there's 2 conditions that have to be met. So the first one is any point in time as likely as any other for an event to occur, like vehicle arrival. You can't say that it's more likely to be in the front end of a time interval than the back end necessarily. And then the occurrence of an event does not affect the probability of the occurrence of another event. If you get 3 cars at the front end, it doesn't necessarily mean you're going to get a bunch of cars at the front end and none at the back end. Or you get 3 cars at the front end, you're going to continue to get 3 cars for every time interval from there on. So anyway, as it says, the arrival of one vehicle at a point in time does not make the arrival of the next vehicle within a certain time period any more or less likely. So just truly random. You know, when I assigned those of you, the students that didn't ask to be in a group to groups, I went online and I just got a random number generator, and then I lined up all the names, gave each name a number, and then as the random number came up, that's how I put you all in groups, just as an example. So a model that fits this description is the Poisson Distribution. And so I don't know if any of you in this class speak French. I took French in high school, a million years ago. And so I like to say Poisson. It's kind of an interesting word. And I think Poisson was a person who came up with the equations and the Poisson distribution. If you've seen this before, so in any event, it's, as it says here, it's a discrete distribution as opposed to continuous, and commonly referred to as a counting distribution, and it represents the count distribution of random events. So it's just one way of looking at and trying to get your arms around the random arrival of vehicles in the case of traffic analysis. So I put these slides together when I did the class previously, and I found this image here. Now, I know Dr. Seuss has been in the news lately. This is not one of the books that they pulled, but I'm guessing that some of you may have seen or read this book when you were a kid. Poisson 1, Poisson 2, Poisson rouge, and Poisson bleu. 1 fish, 2 fish, red fish, blue fish is a very famous Dr. Seuss book. So when I saw this image, I thought, oh, okay, I'm going to grab that, because obviously poisson in French means fish, or is used for fish or seafood, I guess. So there's an equation for a Poisson distribution that you see here, and I know this is pretty much the same color as the little book image I put here, but here's the yellow highlight, and it's equation 523, which I believe is this equation here that I've put in along with the definitions. Basically, I've taken what's in this slide and put it into this document here. And so the Poisson equation is the probability of exactly n vehicles arriving in a given time interval t is equal to this expression here, and the terms in there, lambda, this is a lambda, I believe, refers to the average arrival rate of vehicles, and that's in vehicles per unit time. So units are important here. As we go through this, you'll see in the problems that we work, because units could be expressed in different sorts of things. Vehicles per, in some of the calculations, they're vehicles per second. Other times they're vehicles per minute or vehicles per hour. And N, of course, is just the number of vehicles. It doesn't have a unit. And then T is the selected time interval. And of course, the time interval could be, again, seconds, minutes, hours. So in any event, that's the Poisson equation that we'll be using. So the best way to kind of to go through the use of how this equation is used is to just go through a couple of examples. So this one is built into the slides, and it's basically example 5.4 in your book. And so, basically you start out with a 1 hour traffic volume is 120 vehicles. So you get 120 vehicles in an hour, during which the analyst is interested in obtaining the distribution of 1 minute volume counts. So how are those 120 vehicles going to arrive? And they're going to use Poisson to help determine that. So if you look back at the equation, what you often want to do is see this lambda t. If you figure out what lambda t is, you can put that into the equation. You know the number, the number of the vehicles and the time interval. So basically, you want to be able to put do the lambda t calculation so that you can do the Poisson calculations themselves. So in this case, lambda is the arrival rate. They give that to you. It's 120 vehicles per hour. And you can change that into vehicles per second by dividing it by 3,600, and you get 0.0333 vehicles per second. And so therefore, the lambda t is the 0.0333 times 60 seconds, because they're looking for, they talk about 1 minute volume counts. So you multiply it by 60 seconds and you get 2 vehicles. So lambda t equals 2 vehicles. Or you could do the same calculation again. Units matter, right? So you could say that you've got 120 vehicles per hour and you've got 60 minutes per hour. So that's 2 vehicles per minute. And so then therefore lambda t equals 2 vehicles per minute times 1 minute instead of this 60 seconds. And you still end up with 2. So then what you do is you plug the lambda t into your equation. I have the equation over here on my document here. And so you take the lambda t, which is 2, and you start out with what is the probability of 0 vehicles arriving in a given time frame. So you put in 2 for your lambda t, and that's to raise to the power of n, which is 0, and then e to the minus lambda t, which is 2, and then divided by n factorial, which is 0 factorial, because you're looking for the probability of 0 vehicles arriving. So obviously, any number raised to the 0 power is 1. Any 0 factorial is 1. And you just do the calculation for e to the minus 2, and you end up with 0.1353, or roughly 13.5% is the probability that 0 vehicles will arrive. And so when you're looking for the probability of exactly n vehicles arriving in a 1 minute interval, you do the calculation, the same calculation, but now you do it if you want to know what the probability of 1 vehicle arriving is. You do that same calculation. Now you've got 2 raised to the power of 1 here, and you've got 1 factorial. You end up with a little over 27%. And if you multiply that by the 60 minutes that you have in the 1 hour, though you have 60 1-minute intervals, you end up with, on average, a little over 16 1-minute intervals where you will have just 1 vehicle arrive. You do the same thing for 2. And interestingly, if you look at the calculation for 2 vehicles, it just so happens that it ends up being that same 0.2707. You can see because of the way that these, the 2 factorial and 2 raised to the power of 2 kind of cancel each other out, and you end up with the same number. But then when you go to 3, it changes again, and you've got 2 to the 3rd power multiplied again by that e to the negative 2, and then divided by 3 factorial, and you end up with just over 18%, or 10 1-minute intervals. And it says, and then as it says here, and so on. So you move on, and this is a you can use programs to do these kinds of calculations for Poisson distributions, where you have the arrival rate, you've got the time of 1 hour or 60 seconds, and then vehicles per second here, and you can see that the values that we just calculated, 13.5, 27, a little over 27, a little over 27, a little over 18 are all here. This is the cumulative value. Ultimately, that's going to end up to 1, because this is all about percentage probability. And you can see that the frequencies start out at 8 1-minute periods on average, to 16, to 16, to 10, to 5, to 2, and then it gets really, really small and tails off as you get out to your the number of vehicles being 10. So let me just stop here for a second and say, what now you might say, well, why is this important? Well, what's important is to know that in any 1-minute period, the likelihood of you getting, say, 6 vehicles showing up in any 1-minute period is less than 1% here. So that can help you when you think about, okay, how much storage area, if you're talking about vehicles arriving to an intersection, say to make a left turn, you might say to yourself, well, I need to have storage for about, if the cycle length of the signal is about a minute, I need to, if I have storage for 6 vehicles in the left turn lane, I'm probably pretty good. So this is the kind of thing that this kind of information is used for. You can also obviously show, that's the table form, this is the graphic form that shows the distribution of arrivals. There's 8 1-minute periods within the 60 that no cars arrive, and etc., as we calculated previously. I just, and these fish are here just for interest, if anybody's wondering. So I just put them in. Just once I grabbed an image, I decided to throw a few of them into the slides here. So because we continue to talk about Poisson. So now you can do different things and calculate things in different ways using the Poisson distribution. And so, for example, what is, using that same example, the 120 vehicles arriving in an hour, et cetera, what's the probability of between 1 and 3 cars arriving in 1-minute intervals? Okay, what's the probability? So there, what you would do is you would figure out what the probability of 1 vehicle arriving is, plus the probability of 2, plus the probability of 3. And so, and if you recall, for 1 and 2, we were right around just over 27%, and we were right around 18% for 3 vehicles. So you just add those up. And so the probability of between 1 and 3 cars arriving in a 1-minute interval is about 72%. So once again, you can see how this kind of information could help plan how you prepare for the number of vehicles that are potentially going to arrive, even in a more randomized assumption of vehicle arrivals. You can also say what is the probability of more than 6 cars arriving in 1-minute interval. That was a little bit what I talked about before in using the information, but you can do a calculation to determine what the probability of more than 6 cars arriving in a 1-minute interval. Excuse me. So the way you do that is you just take 1 minus the probability of 6 or less vehicles. Now, this is interesting. So what you're basically doing is you're just taking the probabilities of everything 6 and below. But the one thing you got to remember, look at how many probabilities are listed here. 1, 2, 3, 4, 5, 6, 7. So they're saying what is the probability of of the number of vehicles being 6 or less. Remember, you don't want to forget about 0 vehicles. Sometimes you might just go, you might just do 1, 2, 3, 4, 5, and 6 and forget about 0. But 0 is pretty significant. It's 13%, given the arrival rates, et cetera. So you take those, there's that 13.5% again. Here's the two 27%, there's 18, and then you see these smaller numbers here. So you add all of those up, and they add up to 0.995. And so what you do is you take 1 minus that, and you end up with 0.005, or 1/2 of 1%. So the probability of more than 6 cars arriving in any 1 minute interval is about 0.5%. So it's not going to happen very often. So again, this is how these kinds of calculations are used to help. So here's the Poisson guy. I think he's from the, I looked him up a while ago. I can't remember, but he's been around. He was around many years ago. But so it's important to remember that when you have a Poisson distribution of vehicles, it implies that the time intervals between the arrivals of successive, there's a distribution of the time intervals between the arrival of successive vehicles, or the headways. There is a distribution of headways. And again, this gets back to the reminder that headway is a measure of time, not a measure of distance, okay? And so what makes this important is this, something that's listed in your book and is also over here on this document, is what they term as the negative exponential, and this helps in solving some problems that we'll be working on here. So so you demonstrate this issue of headways by now introducing the concept of flow into the Poisson equation, Q. You're instead of lambda with the arrival rate, you're now talking about the flow rate. And so here they're assuming your flow rate is in vehicles per hour. So if you divide that by 3,600, you get it moves into vehicles per second in terms of this equation. So then you can substitute that into, Q over 3,600, flow over 3,600 for lambda into the equation. I think it was it 523, the original Poisson equation? Sorry, I'm going to go back real quick. Yeah, 523. So you can substitute it into 523, and when you do that, you end up with the equation 525 here. But even and so that is just another way of expressing the Poisson equation. But you can take that one step further when you talk about this negative exponential, and that is the probability of having no vehicles arrive in a time interval length t is equivalent to the probability of a vehicle headway h being greater than or equal to the time interval t. In other words, if there's not going to be any vehicles arriving in a time interval, then that means that the headway has to be, in that case, has to be greater than the time interval itself. Otherwise, a vehicle would have shown up during that particular time interval. So based on that, if the probability of 0 vehicles is the same thing as the probability of the headway being greater than or equal to t, and so you can put that into that previous equation that we just, the 525, and assuming that zero, assuming zero, you end up with just E raised to the negative QT divided by 3,600, because if you're, what you're doing is you're putting in zero into the equation. So this distribution of vehicle headways is known as the negative exponential distribution. So we'll go over a couple of problems that show how this can be useful in solving the problems. So let's do that. The negative exponential example, it's similar to example problem 5.6 in your book, so you can refer to that as well. But let's assume that vehicle arrivals are Poisson distributed with an hourly traffic volume of 360 vehicles per hour, okay? So this is what you know. You've got a traffic flow of a queue of 360 vehicles per hour. So, and that's very common. As we were saying before, flow is often expressed in vehicles per hour, okay? So now what they're saying is determine the probability that the headway between successive vehicles will be less than 8 seconds or between 8 seconds and 11 seconds, okay? So how do we use the negative exponential to be able to solve this? Well, let's take a look. So by definition, the probability of the headway being less than the time interval is equal to 1 minus the headway being greater than or equal to the time interval. That's what we just said. That means if in fact there are 0 vehicles arriving, then the headway has to be greater than the time interval, okay? And so you basically say, if you substitute what they ask for here is anything that the headway will be less than 8 seconds. So you substitute that in here. The probability of the headway being less than 8 seconds is 1 minus the headway being greater than or equal to 8 seconds. Okay, that's just another way of expressing that, and that's how you use the equation 526, the negative exponential. So basically, that equals 1 minus, we use the equation E to the negative QT divided by 3,600. So they gave you Q, which is 360. They're asking you for the probability of it being less, the headway being less than 8, and then divided by 3,600. And so you calculate that out. It ends up being 1 minus 0.449 basically. So the probability of the headway being less than 8 seconds is basically 55%, right around 55%. So you can see, and now we go back to the original problem. It says, what's the probability that the headway between successive vehicles is less than 8 seconds? Now they're asking, what is the probability of the headway being somewhere between 8 and 11 seconds, basically. And so you go to get that, you're basically saying that equals the headway that equals the probability of the headway being less than 11 minus the probability of the headway being less than 8. Okay, so this side of this part of the equation we just calculated, which is the 55, roughly the 55%. And now what you do here, once again, you use the negative exponential by saying this value here, the probability of the headway being less than 11 is the same as 1 minus the probability of the headway being greater than or equal to 11. So you do that calculation, you use the 360 again, and the 11 divided by 3,600, you calculate that out. And so the probability of the headway being between 8 and 11 seconds is about 11.5%. So that's how you use the negative exponential to be able to help you solve some problems related to the headway of vehicles, which is an important concept as you're doing for traffic analysis. And then you can also see that graphically, the negative exponential for as time goes on, the probability of the headway being greater than or equal to the time interval, it drops over time. It starts out high down here at near 0 time base. And as you get out past 30 seconds, the probability becomes lower and lower. So I'm going to go over a couple of other problems. I'm going to back up and do just more of a straight Poisson distribution problem, not so much a negative exponential problem that we just went through, because that was built into the slides. So I was going to back up and do example 5.5 from your book here. But before I do that, are there any questions that anybody has regarding this material that we've gone over at this point? Again, this is showing the importance of understanding a randomized arrival rate for vehicles, because that's a more realistic way to look at traffic analysis rather than just assuming everything is uniform. Okay. Well, like I say, this problem, example 5.5, backs up a little bit, and it's just looking at more at the Poisson equation itself. And so you read the problem up here at it's the traffic data are collected in 60-second intervals at a specific highway location shown in the table. See, these time periods, they go from 12 noon to 12:15 p.m. So they took 15 observations, 1 minute each. And then each one of those minutes, they observed a number of vehicles in that arrived during that 1 minute period. Okay. So assuming the traffic arrivals are Poisson distributed and continue at the same rate as that observed in the 15-minute time periods shown, what is the probability that 6 or more vehicles will arrive in each of the next 3 60-second time intervals, basically from 12:15 to 12:16, 12:16 to 12:17, and 12:17 to 12:18. Okay, sorry. So you've got all the numbers here from 12 o'clock to 12:15. And so if you add up all these numbers, as it says down here, it's a total of 101 vehicles arrived in the 15-minute period, okay? So therefore, the average arrival rate, or lambda, is 0.112 vehicles per second, which would be, 101 vehicles divided by 900 seconds. 900 seconds would be 15 times 60, right? 15 minutes times 60 seconds. And then you would, as in the other examples that we went over, you can apply the equation, the Poisson equation here. I think it's 523 here, to find the probabilities of exactly 0. Don't forget 0, 0, 1, 2, 3, 4, and 5 vehicles arriving. And so when you do that, you've got the lambda of 0.112 vehicles per second, and you've got the t, the time period is 1 minute or 60 seconds. And so therefore lambda t, as they show down here, is 6.733. So I'll move on to the solution itself. The second slide here gets into the solution. So you can see you use the equation here. You use 6.733 as your lambda t, and you use it here, and you raise it to the power of n, and then you put it into the logarithmic function here, and then you use the number of of, you put n factorial as the denominator. So you do that for all 5, you know, and you can see, you know, here we use 0, 1, 2, 3, 4, and 5. The lambda t is the same for all of them, 6.733 throughout. What changes is the n value, right? Because you go from 0 to 1 to all the way to 5. And so the summation of the probabilities of 0 to 5 vehicles will arrive in any given 60 second time interval is summing all of these values that you calculated, starting at 0.0012 to 08 to 27 to 06 to 102 to 137. You add all of that up and you end up with 0.3358. So 1 minus that, this is the probability that there will be 5 or less vehicles. And so if you take that probability and subtract it from 1, that will give you what they asked for, which is the probability that there will be 6 or more arrivals in 1 minute. So you take the 0.333, basically the 33.5% here, you subtract it from 1. And so the probability that you're going to get 6 or more in a 1 minute time interval is just over almost 2/3, 66.42 or 0.6642. So now they also, now that they asked after that, they said, what is the probability that 6 or more vehicles will arrive in 3 successive time intervals? And again, you can see how this applies to how you analyze things like intersections and so forth. So to figure that out, you basically, it's just the product of the probabilities. And so the probability is 0.66. And so you just you basically raise that to the 3rd power, or basically 0.6642 times itself 3 times. And when you do that, you end up with a probability of 0.293, or just a little bit over 29%. So there's a fairly reasonable probability that you're going to get 6 or more vehicles to arrive in 3 successive time intervals. So you can see, given the circumstances of this particular problem, you've got to think about the fact that, you know, you're going to have multiple vehicles more than 6 or so. And if, like, you're trying to figure out whether you need enough storage at an intersection or whatever, this can be helpful in trying to plan for that. So that's more of a straight Poisson distribution problem, not necessarily using the negative exponentials there. I thought I'd go over practice problem 5.2 because this is interesting, because it does, it kind of relates back to a previous chapter when we were talking about, you know, reaction time and stopping time for a vehicle. So it's kind of interesting. I thought it was interesting to introduce that concept here in this chapter 5 when we're talking about arrival patterns for vehicles. So let's go through this one because I think it's pretty instructive. So this problem says a vehicle pulls out into a single lane highway that has a flow rate of 300 vehicles per hour, Poisson distributed. So you have a queue of 300 vehicles per hour. The driver of the vehicle does not look for oncoming traffic. Well, that's not a good thing, but that's what the problem says. So let's go with it. Road conditions and vehicle speeds on the highway are such that it takes 1.7 seconds for an oncoming vehicle to stop once the brakes are applied. So if you did all those calculations we did in previous chapters 2 and 3, you would end up with, you know, a stopping time of 1.7 seconds. So they're not giving us all of the design speed and speed, et cetera. They're basically just saying, you know, that it's going to take 1.7 for of stopping time. And then, as you recall, assuming that a standard driver reaction time is 2.5 seconds, and it says go back to chapter 3 on that, and ignoring the length of the vehicles, which will just have a small influence on the results, what is the probability that the vehicle pulling out will get in an accident with oncoming traffic? Okay, so kind of interesting. What is this? You know, if we know it takes, in essence, it's going to take 4.2 seconds to stop a vehicle, right? Because there's the 1.7 seconds of stopping time and the 2.5 seconds of reaction time. Okay. So the solution here talks about how the Poisson process can be used to arrive at the time spacing between the vehicles, okay? Because that's really the way to be able to solve this problem. It's about what is the spacing between vehicles and what is the likelihood that a driver that's not looking is going to actually not be able to make it. And so it's, as it says, as we just talked about, it says with 1.7 seconds required for a stop and 2.5 seconds for a reaction time. So that's a total of 4.2 seconds. An accident will occur when the vehicle headway is less than that 4.2 seconds. If two successive vehicles are less than 4.2 seconds apart, then you're probably going to have an accident because this guy's going to pull out and not pay attention. Okay. So if you use equation 526, this is, again, this becomes the negative exponential here. If you use that equation 526 with t equaling the 4.2 seconds and the flow equaling the 300 vehicles per hour, you can, well, I'll do that. So basically what you're saying is, what's the probability of the headway being greater than or equal to 4.2 seconds? And so to be able to calculate that, you put the flow in, e to the minus 300 times 4.2 divided by 3,600. You crank that out and you get 0.705. So they're saying with this, the probability that the time headway will be less than 4.2 seconds, and thus the probability of an accident is 1 minus that. So if you basically, the probability of the headway being less than 4.2 seconds is 1 minus the headway being more than 4.2 seconds, which you just calculated up above. So the answer to the problem is that there is 1 minus 0.075 equals 0.295. So you've got a 29.5% chance of an accident because, and so I think this, I wanted to go over this problem because it shows how you can use the negative exponential and the concept of headways to solve various, you know, transportation related problems. Now I would say this is a little odd problem because you're not, you know, most people pulling out into the road are going to look as opposed to not. But I suppose you could say if there were some restrictions on vision or whatever here, that might be an issue. So in any event, that is what I wanted to cover specifically about the class today. I think that was the last problem I had. Yeah. And so what I've gone over there is a couple of problems that are focused on Poisson distribution itself, a couple of problems that are on the negative exponential, at least two of your homework problems. One is on the Poisson distribution, one's on the negative exponential. And then next Tuesday, we will go over kind of queuing theory. And queuing theory is a little bit different. There's really no equations that are used on the problems in the queuing theory that we'll go over on Tuesday. You'll see that. And the problems that I would just let you know, if you want to look ahead, example problems 5.7 and 5.9 are a couple of problems that we're going to go over on Tuesday. And it really is more about matching up arrivals and departures. See, so far in today we talked about a distribution of arrivals of vehicles. on Tuesday, we're going to start talking about both arrivals and departures, right? And if arrivals for any period of time are greater than departures, think about it. Think about a parking lot, right? If you've got more cars coming in than cars going out, ultimately you're going to end up with a queue. You're going to end up with a queue of vehicles, and that becomes really, really important in transportation analysis. So that's what we'll be doing on Tuesday, is we'll be adding in that that concept of the interactions between arrivals and departures. So we'll be doing that Tuesday. So the last thing I wanted to go over today in today's class is I threw this slide in at the end just to give you a particular, get you thinking about the group papers. As I mentioned before, they are due on April 27th. And so my suggestion would be, as a group, to kind of think about and maybe decide on a subject by the end of the month, by the end of this month, more or less, by the 30th or so. These are not hard and fast dates. I'm not going to check on you to make sure you've done any of these things. I'm just suggesting it. And if you go back to your syllabus in the section on the group papers, there are some suggested topics: transportation safety, technology and the future of transportation, environmental impacts of transportation. Certainly COVID-19 impact on transportation is something that's very, very new, but there's a lot of information out there that you could probably find. And if you have another topic that's focused on transportation issues, we covered a lot of topics in those first couple of classes in chapter 1 and so forth. As far as I'm concerned, go for it. You might want to just check. I say submit for consideration. You can just check with me. I might be able to help you a little bit in terms of maybe you have a topic that's, my thinking is that you might have a difficult time finding information on it or whatever. But I've had in some of the previous papers a topic that's not listed here is we had a group, there was a group that focused in on a particular kind of unusual transportation project here in the San Diego region and did their group paper on that. And went out and they interviewed some of the people working on the project, et cetera. I think that's, there's a lot to learn from that too. So, and then I suggest that, that you would put together kind of an outline. To start with the group paper is kind of divide up how you're going to research it, and, and then, develop an outline, overall for the paper, and then the team members can work on individual section outlines for the paper. To do that, say in the first week of April, and then you probably want to have drafts of your sections if you're going to do them in. You're going to divide up, and different members of the group are going to work on different sections. You probably want to have those sections drafted by, say, around April 20th, about a week before it's due. Certainly you want to have it by then. That way you can allow the team to review, everybody can review everyone else's drafts and make revisions. And then ultimately you've got to combine all those sections that are done individually into a single paper. And I put there how you go about doing that as a group. You can pick an editor, maybe somebody whose job it is to pull the pieces together and put it into a final product, and that sort of thing. But anyway, I just wanted to bring this up today as just kind of I didn't want to just wait until, I don't know, April, if it's the 20th, I didn't want to wait till April 22nd, the last class before the paper's due, and say, by the way, next class the papers are due, even though it's on your syllabus and all. But anyway, like I said, you don't have to follow this guideline, but I thought I just wanted to put something in about this time in the semester. I like to put a reminder in. And then the other reminder to this is that as you're working on the paper, think about how you will present it in like a 12-minute presentation that you would do in a Zoom meeting. We did that last semester. It worked out I thought it worked out really well. And I think it's a good learning experience for groups to for a group to work on making a presentation together like that. So that was what I had to share with you today. Are there any questions about what I went over for Chapter 5, this section of Chapter 5, or any questions about the group papers at all? I don't see anything in the chat box. I'm going to go ahead and stop sharing at this point. Okay. No, it's a little bit early. I think with Chapter 5, it's kind of, you know, I could have moved into queuing theory today a little bit, but I think it's better to just wait on that until Tuesday and kind of cover it all in one class. But like I said, you can look ahead if you want on the homework assignment. And I gave you the two examples, 5.7 and 5.9 in your book, as well as we'll go over example problem 515, which is kind of a bottleneck calculation that kind of gets into the queuing as well. All right.
So Professor, just to clarify, we went over everything except the queuing stuff for the homework, but is queuing on the assignment itself or just the stuff we covered up today?
It is that there's a couple of problems on the homework that are related to the material we're going to talk about on Tuesday. And so you can look ahead if you want to try and get a start on it, but it's just because it's homework for Chapter 5. So, but there's definitely a couple of problems on the homework that we've covered both on Tuesday and today. This, past Tuesday and today.
Sounds good. Yeah.
Okay.
Mm-hmm. Thank you, Professor.
All right. Thanks, everybody. And we will hope you have a great weekend. Oh, by the way, I didn't say it at the beginning. I'm wearing my Aztec shirt. You know, the Aztecs, anybody who follows basketball, they won their first game. It was tighter than anybody thought it would be, but that's okay. A win is a win. So they won their first game in the Mountain West tournament. So I'm happy about that. I'm a big Aztec basketball fan. So anyway, hopefully the Aztecs, when we get back together on Tuesday, they will be the tournament champions of the Mountain West and be all set for the NCAA tournament. So anyway, all right. Thanks, everybody. Have a great weekend. Go Aztecs.